Great, thank you. So you can all see my slides. So good morning, everyone. Welcome to my webinar on low loss electron energy loss spectroscopy. This is going to be a very introductory presentation. And one of the main questions I'd like to address is why someone might want to do low loss EELs and what kind of information we can get from doing low loss EELs. So why do we want to look at low loss? In low loss, we're looking at a region of the electromagnetic spectrum encompassing energies from the ultraviolet down to the infrared of the spectrum. If we're at energies higher than ultraviolet, we're getting into X-rays. This is core loss. This is another presentation somewhere on the YouTube channel. If we want to look below the infrared into the microwave and radio, we don't have the instrumentational resolution to see that far down yet in EELs. So we are limited to infrared to ultraviolet as our low loss region. In this region, we're typically collecting information on the valence electron states of the sample, or in the extremely low loss, going down into the infrared, on the atomic or molecular vibrations that a sample might possess. So if your sample has interesting phenomena that you'd like to learn about that occur in the infrared, the visible, or the ultraviolet regions of the electromagnetic spectrum, then maybe you'll be interested to try low loss EELs and see what it can teach you about your sample. So a basic overview of a STEM EELs experiment. I have a beam of fast electrons. Often in the low loss, I'd like to be monochromated so that I have better energy resolution in my spectrum. I send this beam through my sample. Some electrons are scattered out to a high angle where they are collected by an annular dark field detector to form an image. And many of the electrons continue on through the column and go into my spectrometer. The spectrometer disperses the beam and allows me to collect an EELs spectrum. So as the beam passes through the sample, there are many possible things that can happen. Essentially, the electron beam may scatter elastically, which gives you kind of this diffracted beam. It may scatter inelastically and lose some energy, such as when you excite a plasmon or a electronic transition in the sample, or the electron beam can continue going through the sample without having any noticeable interactions at all. The EELs signal that I'm interested in looking at comes from inelastic scattering events where we're losing energy. And for low loss EELs, typically these are very small amounts of energy transferred from my electron beam to my sample. So my electron beam is something like 80,000 kilo electron volts or 300,000 kilo electron volts. And I'm transferring energy on the order of a few electron volts. So a few milli eV up to say around 50 electron volts of energy. And again, typically we're looking at excitations in the valence band of the sample, or even down to atomic and molecular vibrations. So after the beam interacts with the sample, I want to collect the inelastically scattered electrons using my spectrometer. My spectrometer stretches out my spectrum and disperses the beam onto a camera. I integrate my camera to achieve a spectrum. There are lenses inside the spectrometer that allow me to stretch this spectrum to achieve the high dispersion that I need to do low loss EELs, and to also shift the spectrum up and down in energy so I can place the peaks where I want them to be on the camera. So consider the signals that we get in low loss EELs, very often we want to consider what the dielectric function of the sample looks like. So the signal you get in low loss EELs is really dependent on the dielectric function throughout the infrared to the ultraviolet. So I'm going to take a quick look at some of the basic dielectric function models, first of all. So for a semiconductor or an insulator, the electronic states and transitions within the material can often be described by bound harmonic oscillators, and we might use a Lorentz model. This is a Lorentz model to describe the dielectric function. This peak in the imaginary component represents one resonance. So if you're doing optical spectroscopy, you might see an absorption peak here. This could be, say, a vibrational resonance or a transition involving a bound charge carrier, such as a band gap excitation. The resonance in the sample occurs at a frequency I'm going to call omega naught. There's a dip in the dielectric function. It may go below zero, it may not, depending on the background of the dielectric, this static and infinite dielectrics. And then this function rises again to come back to the epsilon infinity value at high frequencies. So where this rise crosses zero is known as the plasma frequency. And at this frequency, the material can support a longitudinal bulk wave that travels through the material, such as a bulk plasmon or a bulk phonon. In terms of the EELS signal, the bulk energy loss function is proportional to the imaginary component of -1 over epsilon. And we can see the bulk plasmon peak coming out in our EELS spectrum. Now, remembering that this is not sensitive to surface modes, so we will not see surface modes in this simple equation here. Now, if you have a material that is a metal or behaves like a metal, we might instead see a dielectric function that represents the behavior of free electrons instead of bound electrons. The basic model for these materials is the Drude model. Here we have the real part of the dielectric function is highly negative at low energies, and it rises and crosses zero as the energy increases. Where it crosses zero, we have the bulk plasmon frequency, which is again a longitudinal bulk wave similar to the Lorentz model. Then we will see a peak at this energy in our bulk EELS spectrum. So the Kramers-Kronig in a real material, however, the dielectric function description is not so simple, and life is a lot more complicated. So if I take silver, it's a fairly general metal that exists in the transition metals of the periodic table. It's described by a combination of a Drude model and a Lorentz model. So at low energies, a Drude model describes well the negative real dielectric function, but as we increase to higher energies, there is an interband transition in silver, as electrons are now able to jump from the 3D band up to the 4S band. And this introduces a Lorentz oscillator into the model. So the effect of this Lorentz oscillator is to screen the plasma oscillation in silver and causes energy shifts compared to what the Drude model would predict. So essentially the Lorentz model and the Drude model are nice and simple, but life is never as simple as you would really hope it would be. And you need to be a bit more careful when you're looking at what your dielectric function is expected to be for your material. So the Kramers-Kronig relationships describe how the real parts and the imaginary parts of a dielectric function are related to each other. So if you know the real part, or if you know the imaginary part, you can apply a Kramers-Kronig relationship to derive the other part and retrieve the full dielectric function. Now the EELS signal you get is again related to the imaginary component of the inverse of the dielectric function. And so if we can acquire an EELS spectrum that contains only bulk losses, then we can use this component to derive the real part of the dielectric function, and so use low loss EELS, apply the Kramers-Kronig relationships, and retrieve the whole dielectric function of your sample. This can also be done in optical spectroscopy, but the problem with the advantage of using EELS is it has a much wider energy range than optical spectroscopy does. And if we notice this integral goes from 0 to infinity, having a wide energy range can be very advantageous if you want to be accurate in determining the dielectric functions. However, the difficulties with using EELS are that you have other things in your spectrum, such as the zero loss peak, you have surface contributions, you may have retardation effects, you may also have multiple scattering effects, and you need to find a way to remove all of these effects to retrieve only the bulk loss function, which is this imaginary component here. So actually, experimentally applying this relationship is very not trivial, and it can be quite difficult. So next, we're going to look at where some of the peaks in the spectrum come from and what can cause them. So if I look at my low loss yield spectrum, I see I have potentially many different peaks in here. The biggest or highest energy peak is usually the bulk plasmon peak. Typically, this depends on the material that you're looking at. Each one will exhibit a different bulk plasmon signal in terms of the shape of the peak and the location of the peak. So it can, say, be at a few eV for, say, silver, up to multiple tens of eV for different insulators. At lower energy than the bulk plasmon peak, we start to get into band gaps, interband transitions, excitons, retardation effects. All of these I'll go through a bit later. Even low energy, we're starting to look at surface plasmons and surface phonons and other phonons in the material, as well as molecular vibrational modes. Now, the most dominant peak usually in your low loss yield spectrum is the zero loss peak. This contains electrons which did not interact in any noticeable way with the sample. So these are unscattered electrons that entered the spectrometer and provide me with a nice energy reference at zero. So if you have a given sample, you will likely see a small subset of all of these different things. You're unlikely to see all of them for any one sample. But depending on what you study, all of these are accessible. We're going to start off with the bulk plasmon. We're going to start at the high energy side, work our way down to the low energy side. So the bulk plasmon is usually the highest energy signal. It can be thought of as a wave of conduction electrons oscillating back and forth in the sea of conduction electrons. So if you think about the ocean, the waves in the ocean are composed of water molecules that all oscillate together. Just like that, the bulk plasmon is composed of electron density and conduction electrons that all oscillate together. The bulk plasmon is a longitudinal wave traveling through your material. It can exist in metals, semiconductors, and insulators, although all of these are going to have very different energy ranges and very different damping factors, which determine the width of your peak. So the bulk plasmon is a very prominent low loss signal. It's almost impossible to not find it if you know roughly what energy it should be at, and it can be used for several different things, including chemical identification, composition analysis of an alloy, temperature measurements, or thickness estimations. So first, chemical identification. So the bulk plasmon for a given material has a characteristic energy, the plasma frequency, and a characteristic full width at half maximum, depending on the damping parameters of the system. The energy increases with the square root of valence electron density and decreases with the square root of the effective mass. Metal, such as aluminum or silver, for example, might have very low plasma frequencies. Even silver is around 3 electron volts, while an insulator might have a very high plasma frequency in the tens of electron volts. So we compare, for example, 3 different materials. They have very different peaks. So if you have a material that you're trying to identify, the bulk plasmon is a way to do that. Although if it's a very complex material, you may end up with many different overlapping peaks in this region, and it may be challenging to unravel them all. However, if we're looking at an alloy, the bulk plasmon is sensitive to the density of valence electrons in the material. So if your material is an alloy material and the valence electron density changes with the concentration of whatever you're alloying with, then the position and shape of the bulk plasmon peak can also change. So we're sensitive to the chemical composition here. So for example, here we show nickel silicon alloys. As the valence electron density increases, the bulk plasmon shifts to higher energies. And it also, we notice that the height of the bulk plasmon peak decreases a lot and it becomes a lot fatter. This is because as we increase the nickel concentration, we are adding more D states into the material, and D states are screening the bulk plasmon and causing broadening of this peak. But using the bulk plasmon, we're able to identify and locate which areas of the sample correspond to which alloy concentrations. In terms of temperature measurements, the bulk plasmon again is sensitive to the valence electron density. So the valence electron density is a number of electrons per volume. So if you heat up your material and the volume changes, the valence electron density will also change and the bulk plasmon peak will shift. So if we heat it up, we reduce the density, so the volume is expanding, the number of electrons is assumed to be the same. Potentially that could also change, and your bulk plasmon will shift to lower energies. The shifts are actually quite small. We're talking about something on the order of millielectron volts. But it is possible to detect these changes if you set up your experiment very carefully. One of the more common uses of the bulk plasmon peak is probably to estimate the thickness of your sample. So the electron beam, as it passes through the sample, has some probability of exciting a bulk plasmon dependent on the thickness of the sample. So it has a probability per path length. If the sample is very thick, a single electron may also excite multiple bulk plasmons on its way through. This allows us to use statistics, comparing the mean free path to the area under the bulk plasmon peak and the area under the zero loss peak. So for a thicker sample, the zero loss peak is reduced and the bulk plasmon peak is increased in intensity, and we may even see a multiple scattering peak at integer multiples of the plasma frequency. So this allows us to create an estimate of the thickness if we know we have our EELS spectrum, and we can, if we are able to know the mean free path of our material, then we can estimate the thickness. Otherwise, we can estimate a T over lambda parameter, which tells us how thick the sample is related to its mean free path of the bulk plasmon scattering event. So we're going to move on to lower energies and retardation effects. Retardation effects may include something like Cherenkov radiation. So Cherenkov radiation occurs when the electron is moving faster than the speed of light in the medium. So if we look at some common semiconductors such as gallium arsenide and silicon, they have a high refractive index and the speed of light is actually very low. So we're at something like 0.3 times the speed of light in vacuum. Now we compare that to our electron energy at 200 or 300 kilovolts, and this electron is moving at 0.7 or 0.8 times the speed of light in vacuum. So the electron is actually moving a lot faster than light in this medium and can emit Cherenkov radiation. So Cherenkov is something you need to be aware of and be concerned about when your electron beam is moving very fast or when the refractive index of your sample is very high, so that light might be moving very slow. For many semiconductors, for example, the Cherenkov radiation will almost certainly occur because you have this relationship between refractive index, speed of light, and the speed of the electron beam. However, by changing the thickness of your sample, you can reduce or potentially even eliminate Cherenkov radiation. The thickness of your sample to support Cherenkov needs to be kind of comparable to the wavelength of the radiation that is emitted, which is going to be determined by the energy loss. So if you have a very thin sample in the order of 100 nanometers, you may not see Cherenkov radiation at all. But as your sample starts to get thicker, then it's more comparable to the wavelength of light in these regions, and you may start to see Cherenkov in your EELS spectrum. Another type of retardation effect that you might see in your EELS spectrum is the guided light or whispering gallery effect. These are essentially the electron beam can excite a photonic electromagnetic wave. This is basically similar to those used in fiber optic communication devices. So if you have a thin dielectric material, it can support a guided photonic wave traveling through this material, and the electron beam may be able to excite this. The light wave may be guided if the sample has a high refractive index through total internal reflection of the edges of the sample. These guided light modes occur when we have high refractive index or high energy electrons, similar to Cherenkov, and for relatively thick samples that can support a confined guided photonic mode. This may be seen as a series of peaks in the bandgap region of your spectrum. So that's kind of one marker to look out for. If you confine this guided light into a nano or micron scale sample, you may get a photonic standing wave. These are the whispering gallery modes. And if you do a spatial EELS map, you may actually be able to see these whispering gallery modes. So depending on the experiment you're doing, you may be annoyed by these peaks in your spectrum, or you may be very interested in learning about the standing waves and the guided modes that your sample can support. As we continue sort of in a similar region of the spectrum, we're starting to see interband transitions in our sample. Interband transitions are essentially when an electron in the valence band can be excited to a state in a conduction band, or in the case of, for example, metals, from a lower energy D band to a half-empty higher energy S band. So in EELS, we can see both direct and indirect bandgap transitions. So very useful for semiconductors or insulators. We will also see the momentum transfer if you care to do momentum resolved EELS. And depending on the material, we're looking at bandgaps typically like around 1 eV, 10 eV, somewhere in the middle. You think about the bandgaps of your classic semiconductor material, that's what we're looking at. So to measure a bandgap in an EELS spectrum, if we look at our spectrum, this is raw data of silicon dioxide, we see an onset here. But first, and this corresponds to our bandgap excitation, after which many valence electrons are able to transfer to the continuum of states in the conduction band. So it's an onset rather than a peak. To measure this bandgap, first we need to subtract this background. Often we're sitting on the tails of the low loss spectrum of the zero loss peak in the low loss. And subtracting these tails is very important for doing bandgap measurements. So if we fit and subtract the tail of the zero loss here, we come out with something near zero. We take the first rise in this spectrum and we fit a line to it. And where this line crosses zero, we have our measured bandgap. There's a lot of things to think about when doing a bandgap measurement, including the resolution of your spectrum and the zero loss peak tails, the retardation effects that I just mentioned, as well as quantum confinement effects. So if you have your semiconductor in a nanoparticle, the quantum confinement of the nanoparticle may actually change the bandgap, and you may not get the value that you would expect from measuring a bulk material. Something else that may occur around the bandgap energy is an exciton. So the exciton is a bound state. It's a state where an electron is excited to the conduction band, and it is bound by Coulomb forces to a hole in the valence band. And these typically present in EELS as a strong, sharp peak at the onset of the bandgap excitation or another transition. And if all you're interested in is knowing where your bandgap is, maybe you find the exciton peaks a little bit in the way and annoying. But also there's been some very interesting work regarding the coupling of excitons to other resonances in the sample, such as plasmon states, and the interesting things we can do by coupling excitons. As we travel to even lower energy in our spectrum, we start to come across surface plasmons and phonons. The surface plasmon is So the bulk plasmon is a wave of conduction electrons in the bulk of the material. The surface plasmon is a wave of conduction electrons traveling across the surface of your material. So the surface plasmon polariton is a quasi-particle. It has a mixture of mechanical energy in the motion of the conduction electrons and electromagnetic energy in the photon-like fields that it carries with it. And it's sort of the coupling of these two behaviors gives you the polariton. So if we take your sample to support the surface plasmon polariton, usually you must have conduction electrons, such as something like silver or gold, or even highly doped semiconductors are very good at supporting surface plasmon polaritons. Now, if you have a thin film, such as you often do in a TEM, then you may get two surface waves on the material, one on the top side and one on the bottom side. These are coupled across the film and form symmetrical and anti-symmetrical charge distributions. So these are oscillating charges, and they may be either the same or the opposite on either side of your thin film. Now, if you take these surface plasmons and you confine them into a small nanoparticle, or you take your material which supports them and confine it into a small nanoparticle, we start to see localized surface plasmon resonances. Again, these are standing waves of electron density, which are oscillating on the surface of your nanoparticle. In EELS, the electron beam interacts with the electric field of the resonance to excite a mode. The properties of these modes will depend on the geometry, the material's dielectric function, and the surrounding environment. And there are many, many examples of these. If you'd like to talk more, I'd love to talk about plasmons, so let me know. Now, if multiple plasmonic nanoparticles are brought into close proximity with each other, these have evanescent fields. These evanescent fields interact with each other, forming bonding and anti-bonding resonances. These are going to change the energy of the resonance compared to the single nanoparticle. So there's going to be your single peak in EELS is going to split into two peaks at bonding and anti-bonding at lower and higher energy. And also the spatial map in EELS will be different for these two different types of modes. And again, you introduce multiple different nanoparticles. You can continue this hybridization to many, many, many different peaks, many different hybridizations of charges. And there's a lot of work going into understanding these modes and how they couple to each other. If we continue going to low energy into the infrared, we begin to detect phonons in the material if we have an instrument with high resolution. The phonons are collective lattice vibrations. They can be either longitudinal, where we're looking at a longitudinal wave oscillating back and forth, or they can be transverse, something like a skipping rope, where you have a transverse oscillation up and down, for example. They can also be optical or acoustic, where the acoustic phonons have no net dipole moment. The optical phonons support a net dipole moment, and so can couple to light, which is, I think, why they're called optical phonons. Now, these four different types of phonons can all exist in the bulk in your material, depending on the material. There's some very, in different lattice orientations, different phonons with different wave vectors will propagate. So if you're doing an EELS experiment to look at the phonon distribution, you need to think about the wave vector of the phonon, the wave vector of your electron beam, and the crystal wave vectors and orientations related to your electron beam. There's some really interesting science to be done here in relating the phonon excitation, the crystal structure, wave vectors, and how they impart momentum into the electron beam. Now, similarly to the surface plasmon, an ionic material might support a surface phonon polariton. So if you have a crystal lattice which has ions of different charges in the unit cell, then we may be able to support both the optical phonons and surface phonon polaritons. The phonon polaritons are quasi-particles, again, similar to the plasma polaritons. They are a mix between electromagnetic oscillations and the mechanical vibrations, but this time it's the vibrations of the ions in the lattice. Again, these properties depend on the geometry of the material, the dielectric of the material, and the dielectric of the surrounding environment. With the phonon polaritons, we're looking in the Reststrahlen band of a dielectric material, which occurs in between the transverse optical and the longitudinal optical bulk phonons, where the real part of the dielectric function dips below zero, which is a necessary mathematical condition for a material to support surface modes. So there's a lot of new research coming in, especially with the high resolution instrumentation, like the NEON machine that we're hope to be getting soon. It's a lot of new and interesting research on the behavior of phonon polaritons and on their coupling as well. Finally, in the extreme low loss region of the spectrum, into the, say, the mid and near infrared, we start to sample in a molecule. You may have many different waggling, rotating modes as the bonds in the molecule change. And we can begin now with high resolution instrumentation, we can begin to pick up these modes. So this means, for example, that we can detect hydrogen in the electron microscope through its vibrational modes and bonds with other atoms. Hydrogen is something that's typically very difficult to detect, but using vibrational eels, we can begin to detect where it is and what it's bonded to. This is kind of like a complementary technique to Raman and infrared absorption spectroscopy, in that we're probing the molecular vibrational modes. We may have nanoscale resolution. We do need to worry a lot about beam damage. We gain some advantage from delocalization of the signal from these modes, which means that it's possible to leave the electron beam outside the sample and still acquire information from the sample. Now, the final peak in our spectrum is usually the largest peak. This is the zero loss peak. The zero loss peak is consisting of electrons that have scattered elastically or have scattered with such small energy losses that we cannot detect the energy loss. It's located at the zero of the energy loss spectrum, so it is great for having a calibration reference. And it's the width of the full width of the zero loss peak is going to determine the resolution of your spectrum. And the shape of this peak determines what you can see in the low loss and how low you can go into the low loss. We can also refer to it as the point spread function of our spectrum. So the resolution of our spectrum is given by our full width at half maximum. If the peak is very fat, then it's going to hide any signal from your material that may occur in the first few EV. So if we want to start probing in the infrared, we're looking at less than 1 EV. We need to have a very skinny zero loss peak to even be able to see the signal here without it being overwhelmed by the giant zero loss. The tails of the zero loss peak are also important to what you can see in your spectrum. So if these tails are very fat, then you will not be able to see peaks that are overlapping in energy. So right now we're really pushing the instrumentation resolution, both with the NEON and the Ultimono, the monochromator, to try and narrow the full width at half maximum of this peak so we can see lower and lower energies in our spectrum and probe even more interesting physics. There are many ways to try and remove the zero loss peak, such as deconvolution techniques, subtraction techniques, fitting and subtraction of the tails, as is done for the bandgap measurement. But overall, this is one of the most prominent peaks in your low loss region. And it is the final peak that I'm going to talk about today. So I'm going to finish off and leave you with some useful textbooks that I've been using throughout my PhD and find very useful, including Ray Egerton's Eales Bible and several references on electron microscopy in general. I will also recommend, for those of you who are interested in doing low-loss eels, that there are several textbooks available on either solid-state physics, the physics of surfaces, the optical properties of solids, which is a very, very relevant in the infrared and visible region of the spectrum, as well as some solid reference textbooks on electrodynamics and optical constants. And I will leave it at that and open it up for questions.
Great, thanks, Isabel. So everyone, please put any questions you have in the chat. So the first question is, do you have any experience detecting the helium K edge? I work with samples that have helium embedded in silicon oxide and struggle with deconvoluting the helium K from the silicon plasmon.
I have never looked at a helium sample. I think I've seen in a conference somebody looking at helium bubbles, but I've never looked at it myself or tried to deconvolve that edge.
Can you make any comments, Isabel, on what maybe some things you could do when you have overlapping edges in the low loss region?
In terms of
separating the signal, is it, I know
Yeah.
you can do it with core loss, but what about low loss?
Yeah, so you can try something like a deconvolution technique or peak fitting. There's nonlinear least squares fitting, an LLS, that you can use to try and fit your peaks if you know what shape they are. If you have a reference spectrum, that can help a lot. So if you have a reference from the pure material, you can try and fit that to your material. Something like, some people have tried something like PCA or ICA, the principal component analysis. These are not great in the low loss just because of the presence of the zero loss peak. But if you can cut that out or remove the zero loss peak, you may be able to try these analysis techniques as well.
Okay, I have a question. Could you comment maybe on when the neon comes, what, based on like the presentation you gave, kind of what it's going to be good at, and maybe some experiments that might be able to be done with that instrument that we presently can't do with the instrumentation that we have? Yeah,
so I think, one of the biggest advantages is the energy resolution of the neon instrument. So the Ultimono seems so far to get us down to around 30 millieV resolution, full width half max of the zero loss peak. The neon is expected to be somewhere sub 10 millieV resolution, like 5 to 10. So we're really able to get into the surface phonon modes and the vibrational modes that we can, even potentially mid-infrared plasmonic modes that we cannot access right now with our Titan